Hi everyone, my name is Diaz, and today I will be speaking about the neurodevelopmental lead exposure alters the sensitivity of dopamine system using catalepsy studies. A basic overview of what I will be speaking about today is the background on lead toxicity, developments of the dopaminergic system in rodents, catalepsy behavioral tests, and implications of early lead exposure on the dopaminergic system across lifespan. So the first thing we have to understand is how exactly is blood lead level measured. This is done through micrograms per deciliters, where 100 milliliters is equal to 1 deciliter. What's very interesting here is that low blood levels are very detrimental to the brain, and high levels are also severely detrimental. One would think that high lead levels are bad and low lead levels are better, but in this case, it's not. That's not it. Low levels particularly disrupt growth, sensory systems, etc. When we then take a look at the comparison between children and adults, we find that children are found to be more problematic to lead exposure than adults because children's brains are being developed early on in life. And if lead gets in, it can disrupt a lot of these systems that can carry problems for the rest of their lives. When an adult is exposed to lead, they already have a developed brain and are predominantly protected. However, children absorb a lot more than adults, and it gets right into their physiological systems with greater concentration and greater impacts. Now that we understand this, let's take a look at the chronological review of the United States CDC threshold for lead poisoning interventions. We can clearly see as the year goes on from 1960 to 2012 that CDC blood lead levels listed as a threshold seems to be decreasing every time the CDC revises it. However, since 2012, 5 micrograms per deciliter hasn't been reviewed to be detrimental to the human health. It's extremely important that this number also decreases. Because if you take a look at effects of environmental contamination, we see that high levels of contamination of lead in the environment is not good. But from a public health and epidemiological model, they look for lower levels in the environment and they say that the job is done. From a neuroscience standpoint, if the brain gets high lead levels, as we've seen with the blood lead levels, it's considered to be really bad, causing encephalopathy, brain disease, and even death. But what's peculiar is that unlike the environment, if the brain gets low levels of lead contamination, it damages IQ and has learning and behavioral problems, and as well as sensory issues. So the brain at low levels isn't spared. We must also take a look at the later effects of lead poisoning. We find that lead poisoning early on in life can cause an increased risk factor for developing schizophrenia, increased risk for drug use and abuse, increased sensitivity to opioid, sensitivity to amphetamines with drug reversal effects. So we hypothesize that neurodevelopmental lead exposure will cause an increased sensitivity to haloperidol behavioral pharmacology test challenge and will increase rates of catalepsy. And this right here is just an illustration of the dopamine system where dopamine is made from the substantia nigra and the ventral tegmental area, and the circuit of interest is that which projects to the basal ganglia. This part right over here. And the reason why we are showing this to you is to show the evidence that dopamine is already established at the embryonic day 12. The physical receptors exist, but the functional connectivity of the brain happens later on, as it can be seen in this illustration. The evidence that we do this test on day 10 is because the system is already connected. So if the system is already connected or disrupted at day 10, then the rest of the rat's dopamine pathway will be inadequate throughout its life. There are 3 different dopamine pathways. The mesocortical pathway, which extends from the substantia nigra and the ventral tegmental area to the frontal cortex. The mesolimbic pathway, which goes to the cortex, the hippocampus, and the amygdala. And the mesostriatal pathway, which goes from the same substantia nigra, ventral tegmental area to the basal ganglia. And that's the one that we will be focusing on for this experiment. There's also different types of dopamine receptors, D1 and D2, where D1 are stimulatory and D2 are inhibitory. And they basically balance each other out in terms of the dopamine signal, but in particular to the mesostriatal pathway, we are interested in the D2 receptor, which are also involved in drug reinforcement and so forth. The method in which we use to test these animals is that we basically injected these animals subcutaneously with either saline or haloperidol in the nape of their neck 1 hour before they were tested on this catalepsy bar test. The faster they came out of the catalepsy, the less sensitive they are to the drug. whereas the longer they take to come out of the catalepsy, the more sensitive they are to the drug. And blood samples were also taken a few hours after testing to determine lead insalts in these animals. Here is just a good example of how this test looks like. When we look to the left side, we can clearly see that the leaded animal, which is given saline, falls off the bar relatively quickly. However, when in comparison to a leaded male, which was given haloperidol on the right, it was found that they stayed on the bar. They stayed in the state of catalepsy for about 3 minutes. And this is just an illustration for the weight of the males and the females. Female controls weighed more than the male controls, and all the leaded groups, even though they were no different from each other, they were found to be heavier than the control groups. As for the catalepsy test, the males and the female controls with saline came out of catalepsy very quickly, but when given haloperidol, they had increased freezing. Comparably, when we look at the male and female leaded animals, they froze more with just a saline injection, indicating some kind of fear response when they were injected. But when you give them haloperidol, there's a 3 times increased freezing compared to control males, and a 2-time increased freezing compared to control females. When we look at the blood levels, there's no difference between the males and the females, except that they have 10 to 15 micrograms per deciliters of lead poisoning detected by day 10 of age, and controls were lead negative. There's a main effect of weight where control male rats weighed less than females, but there were no difference in weight in comparison to the male and female rats that were lead exposed, but overall leaded rats weighed more than the control rats. There was an increase of catalepsy when the control animals were given haloperidol in comparison to control saline, but the more important take-home message is that male rats that were lead poisoned had a 3-fold increase of freezing in comparison to the control males, and the females that were lead poisoned had 2-fold increase compared to the control females, indicating that males that are lead poisoned are more sensitive to D2 receptor antagonists than females, but both lead animals are more sensitive than the controls. We found that as early as 10 days of age, that the dopamine systems for D2 receptors sensitivity is altered as a function of lead poisoning. These findings suggest that across the rest of the rat's lifespan, they would be predisposed to cognitive impairments, learning deficits, motor disturbances, and potentially possessing an increased risk for recreational drug substance use and abuse. And in particular, the kids that are lead poisoned are already coming from financially disenfranchised, low socioeconomic status, and underrepresented minorities, which further increase the risk factor for potential drug recreational use. Conclusions and limitations is that although we only experimented on rats which are postnatal day 10, later assessments of mature rats would need to be tested in this model to confirm these profiles later on in life. We also think that these are very predictive, that we can identify that these profiles can be easily assessed, and they may be good models to evaluate D2 receptor drugs that to maybe block the recreational drug use. And at the same time, D2 receptor drugs might be more effective for cognitive enhancement if these dopamine impacts cause cognitive and learning and memory impairments when they get older. And comparatively, if D2 receptors aren't the way to go, then maybe we can take a look at the other side of the dopamine receptor, which is a D1 receptor, which could be another possibility. Here are my references, and these are just the acknowledgements. The behavioral work was primarily done by myself and Jewel Joseph, and the faculty mentor on this project was Dr. Neuwirth. And just a special thanks to the art department, especially Frederick Fleischer and Michael Capobianco for helping us with the 3D printing of the Catalepsy test chamber. And also thank you to the funding by the SUNY Faculty Development Grant. Thank you.